Yes, friends, welcome once again to the class. And someone had even asked that, how are you such a happy person? Someone was asking, do you think I am happy? It's just a joke. I am not at all a happy person in my life, but still I continue with my work. Anyways, when people say that I am very happy person, I feel very odd. Okay. Nuclear angular momentum, nuclear spin. We had already learned that protons and neutrons possess angular momentum. So they have what? Orbital angular momentum due to motion about center of nucleus, and intrinsic spin angular momentum, which is half h cut, just like electron. We had learned this. This is according to classical model. Okay, we are treating nucleus to be classical entity. We are considering nucleus to be classical entity. Only then we can say such things, that orbital angular momentum, intrinsic spin angular momentum. Okay, because even in quantum system also these things are defined. Orbital angular momentum, intrinsic spin angular momentum, these things are defined for quantum system as well. But in quantum system they are defined in a different manner. Okay, in a quantum system they are defined in a different manner, and in classical system it is defined straightforward. It is very easy to understand these terms. It is very easy to understand this particular term and this particular term. It is very easy to understand classically. Okay, classically it is very easy to understand these two terms. But if we talk about quantum mechanics, then it becomes quite tedious to understand these terms. Okay, but classically what does it mean? Classically, as already told in the previous class, due to motion of the nucleons, that is motion of the protons and neutrons about the center of the nucleus. Okay, about the center of the nucleus, motion of proton and neutron leads to orbital angular momentum, and intrinsic spin angular momentum is on account of the proton. For example, this is proton, so if it spins about its own axis, then we call it intrinsic spin angular momentum. And we have neutron also, it also spins about its own axis, so on account of that it has intrinsic spin angular momentum also. Okay, so these are the things. Now the total, now over here the t is missing. Okay, just put like this, one horizontal line over here. Okay, the total angular momentum of a particular nuclear state, the total angular momentum of a particular nuclear state is the resultant of individual momenta of constituent nucleons. Okay, this will become even more clear when we move forward in the class, and as in the upcoming sessions also this will become even more clearer to you, that total angular momentum of a particular nuclear state. Okay, if we have some particular nuclear state, that is we write the nuclear configuration. Suppose, now how to write the nuclear configuration you don't know, but suppose the nuclear configuration is such that it is 1s2. Suppose I am saying, okay, so total angular momentum of particular nuclear state, this is your particular nuclear state, its total angular momentum will be resultant of individual momenta. Now it has two nucleons, right? It has two nucleons, so two nucleons are there. So nuclear the total angular momentum of this nuclear state will be, suppose that it has one proton and one neutron. Suppose, then what will happen? The total angular momentum of this particular nuclear state is resultant of individual momenta. Okay, you will add the momenta of this proton and the momenta of this neutron. Okay, so that will be the resultant of individual momenta of constituent nucleons. That's what is the meaning of this. So similarly we may have some other configuration. Okay, we may have 80 protons and 96 neutrons. Okay, such system we may have with us. Okay, so in that case, whatever will be the nuclear configuration, you will actually, the total angular momentum of that particular nuclear state will be the sum of individual momenta of these 80 protons and individual momenta of these 96 neutrons. Such will be the situation. Okay, magnitude of the total angular momentum. Okay, magnitude of total angular momentum, how is it given? it is given like square root of I into I plus 1. When you learn atomic and molecular physics, okay, all these terms will be introduced in atomic and molecular physics, but for the time being just remember these things as it is, okay, because I am going to teach in the next month atomic and molecular physics. There these things will become more clearer to you, but for the time being just remember the things as it is. So magnitude of total angular momentum, how is it given? Magnitude of total angular momentum is given as the square root of I into I plus 1 h cut, okay. Now I is your total angular momentum quantum number. These things you must remember as it is. Even if you are not able to visualize these things, still you must remember them as it is for the time being. They will become more and more clearer to you in the upcoming sessions, okay. So magnitude of total angular momentum is given by square root of I into I plus 1 h cut, and I is your total angular momentum quantum number over here. The value of I depends on the type of interaction between the nucleons, okay. What is this I? This I is your total angular momentum quantum number, okay. Now you have already seen over here orbital angular momentum, okay, and spin angular momentum. We have two type of angular momentum, right? Orbital angular momentum and spin angular momentum. So because when we combine these two, when we combine orbital angular momentum and intrinsic spin angular momentum, we get the total angular momentum. So let me write over here orbital, okay, angular momentum plus spin angular momentum, okay, is equal to your total angular momentum, okay. Your total angular momentum will be a combination of these two things, okay. Total angular momentum, now it is not necessary that they will be added. This plus sign does not indicate that they are being added. No, this plus sign doesn't mean they are added, okay. Let me write properly over here, orbital angular momentum in combination with, okay, orbital angular momentum in combination with, okay, orbital angular momentum in combination with spin angular momentum gives total angular momentum. That's what I mean. That's what I mean. Okay. So magnitude of total angular momentum is equal to square root of I into I plus 1 h cut. I is total angular momentum quantum number. Okay. The value of I depends on the type of interaction between nucleons. Your value of I depends on what? Type of interaction between the nucleons. How does the value of I, that is total angular momentum quantum number, how does it depend on the type of interaction between the nucleons? It depends on the type of interaction between the nucleons, because suppose we have one proton over here, we have one neutron over here, okay, they are suppose inside the nucleus, and suppose this proton and this neutron are nearby, and this proton and another neutron, okay, this proton and neutron are far separated from one another, and these are near to one another inside the nucleus. Then in such a situation what happens? In such a situation there will be different type of interaction, and as the each nuclei, each unique nuclei, okay, each unique nuclei I am saying, what does it mean by each unique nuclei? Each unique nuclei just means that we have hydrogen nucleus, we have helium nucleus, we have deuterium nucleus, we have tritium nucleus, okay. So all these nuclei, what happens to them? The value of I will be different for each and every nuclei, because the value of I depends on type of interaction between the nucleons. Different are the nuclei, different are the filling of nucleons, okay. In different nuclei, different the nucleons will be filled in different manner, right? In different nuclei, the nucleons will be filled up inside the nuclei in different manner, in different nuclei. So there will be different type of interaction in different nuclei. So value of I will be different for different nuclei, okay. So value of I will be different for different nuclei. That's what it means. Now LS coupling. Let us understand the meaning of LS coupling. Now this is what your total angular momentum quantum number I vector, and this total angular momentum quantum number I vector is equal to your L vector plus S vector, where your L vector is what, summation of Li vector, that is vector sum of orbital angular momenta of nucleons. Okay, and S vector is what, summation Si vector, that is vector sum of spin angular momenta of nucleons. I am not able to maintain the regularity in making videos because I am also disturbed a little bit. Okay, I am not in a good mood, but still I have to make the videos. So that's how the life is. The life is actually not a smooth path. Actually, it is a very tough path. For some people it might be easier a little bit, but for some people it is really difficult. Anyways, LS coupling. So I is what, your total angular momentum quantum number, and it will be the sum of, in this particular LS coupling, this I vector will be a sum of L vector and S vector. Okay, so in LS coupling what happens is that you suppose you have, let me give you one example. What is the difference between LS coupling and JJ coupling? Let us understand. Okay, difference between LS coupling and JJ coupling. Okay, let me give you one example over here. Suppose I have, this is one proton, this is another proton. Okay, and I have three neutrons with me. So I have a system, I have a complete system consisting of 2 protons and 3 neutrons. Okay, now let us understand the meaning of LS coupling and JJ coupling, and what is the difference between LS coupling and JJ coupling. Let us understand that. Now we have 2 proton and 3 neutrons with me. Now what is there? L vector is equal to summation Li, and that is vector sum of orbital angular momenta of nucleons. Okay, so this is, suppose your this will be the orbital angular momentum will be L1. For this the orbital angular momentum will be L2. Okay, for this the orbital angular momentum will be L3, right? Because L represents what, orbital angular momenta, right? So L represents orbital angular momenta. So this neutron has L4 orbital angular momenta, it has L5 orbital angular momenta. Okay, what about spin angular momenta? Let us let us assume that the spin angular momenta I am denoting by green color. So spin angular momenta of this is S1, spin angular momenta of this is S2. Okay, spin angular momenta of this is S3, spin angular momenta of this is S4, spin angular momenta of this is S5, suppose. Okay, now eventually the what is the difference between LS coupling and JJ coupling, it will become clear to you. Now in LS coupling what happens is that you have to find the total angular momentum quantum number I. Okay, total angular momentum you have to find out. This is the nucleus which we have with us. This nucleus has 2 protons and 3 neutrons. Okay, so we have to find the value of I vector for this particular nucleus. So if the nucleus suppose follows LS coupling, if the nucleus suppose follows LS coupling, then what will happen? Then what will happen is that you will add the L vector first. So the L vector will be equal to your L1 vector plus L2 vector plus L3 vector plus L4 vector plus L5 vector. That is how you will find the L vector. And how will you find the S vector? You will find the S vector as follows, that it will be equal to S1 vector plus S2 vector plus s3 vector plus s4 vector plus s5 vector. Okay, so this is your s vector. Now we have to find out the value of I, that is total angular momentum quantum number. Okay, so how will you find the value of I? This particular value of I, can be simply found out. Add this L vector with this S vector. Okay, add this L vector with this S vector, you will get the value of I. That is what is meant by LS coupling. That is, you have first added all the L's, then you added all the S, then after that you took the sum of L and S. Okay, after that you took it. Now what is a JJ coupling? What is JJ coupling? Now I am telling you the JJ coupling meaning. Okay, so see over here what it is written, what has been written over here. Just have a look at it. Okay, just have a look. JJ coupling, in this case the orbital and spin. Okay, in this case the orbital and spin moment of each individual nuclei are strongly coupled. I is the vector sum of individual j values, that is I vector equal to summation I ji. Okay, let us understand the meaning of this. I am telling you the meaning. Okay, you will understand it in a better way. So suppose we have again the same system. Which system? The system consisting of 2 protons and 3 neutrons. Okay, and suppose again we have the same situation. It has orbital angular momentum L1, L2, okay, L3, L4 and L5, and again spin angular momenta. What about that? S1, S2, okay, S3, S4, S5. These are the spin angular momenta, right? What did you do in LS coupling? In LS coupling you added these and these. Okay, and then you added these and these, and after that you took the L vector plus S vector. But in JJ coupling we are doing in a different manner. In JJ coupling we are first adding this and this when we are writing it to be J1 vector. Okay, then we are adding this and this, we are writing it to be J2 vector. Okay, then we are adding this and this. In JJ coupling I am telling, then we are naming it J3 vector. Then we are adding this and this, we are naming it to be J4 vector. Then we are adding this and this and we are naming it to be J5 vector. Then what are we doing? We are, in order to find the value of I, total angular momentum I, we are simply adding this J1 vector plus J2 vector plus J3 vector plus J4 vector plus J5 vector. In this way we are doing. So this is what is the difference between LS coupling and JJ coupling. Hopefully you understood. Okay, I will be equal to J1 plus J2 plus J3 plus J4 plus J5. Okay, so that is what is the meaning difference between LS coupling and JJ coupling, and that's what has been written in these particular slides too. Okay, that's what has been written in these slides also. Okay, so LS coupling and JJ coupling. I am actually suffering from low efficiency nowadays actually, but anyways we have to continue our videos because I can't stop it. I cannot give it a halt altogether. It will be disastrous, that's why. Okay, so LS coupling and JJ coupling we saw it. So the same things have been written over here. Okay, so this is your what? Total angular momentum quantum number I, and it will be equal to L vector plus S vector, and L vector is equal to your Li vector sum of orbital angular moment of nucleons. S vector will be equal to summation Si vector sum of spin angular moment of nucleons. So we first added the angular moment of all nucleons, and then we added the spin angular moment of all nucleons. So after adding the orbital angular momenta of all nucleons and after adding the spin angular momenta of all nucleons, then we finally added the total sum. We finally added this total sum with this total sum. That's what we do in the LS coupling. But what about JJ coupling? In this case, the orbital and spin, okay, momenta. In this case, the orbital and spin momenta of each individual nucleon. Let me put this to the downward side, okay. So momenta of in each individual nucleon are strongly coupled, okay, strongly coupled. They are strongly coupled. I is the vector sum of individual j values, okay. I is what? I is the sum of individual j values. Thus I vector equal to summation I ji, okay. They are strongly coupled. So I is your vector sum of individual j values. So I vector is equal to summation I ji, where your ji is li plus si. This is your I, okay, not l. This is your I, okay. So ji is equal to li plus si vector. So that simply means that your j equal to l plus minus s, okay. Why is it like this? Because either s can be parallel to l or s can be anti-parallel to l, okay. Because spin is possible in only two direction, right? See, if this is my nucleon, okay, if this is my nucleon, suppose it is proton, then it can spin in only two direction, either clockwise or anti-clockwise. It has only two directions, right? So when if it has only two direction, when it spins like this, then it will have this particular direction according to right hand thumb rule, right? Let me explain it properly on the next page, okay. What I am explaining, what am I explaining? Let me first tell you what am I explaining, otherwise you will confuse. So ji equal to li plus si, and how this, when after I opened the vector sign, after I removed the vector sign, why j equal to l plus minus s has come. So why plus minus has come over here? That's what I am telling you, okay. It was plus li vector plus si vector, it was like this, and when I removed the vector sign and converted it into magnitude, why it became j equal to l plus minus s. Why plus minus has come over here? That's what I am telling you, okay. That's what the reason of that I am telling you. So see, this is what, this is my proton, okay, and suppose this proton is rotating like this, okay. So only two directions of rotation of the proton are possible. Only two directions of rotation of proton are possible. So let us think classically that this particular proton, in this case, it is rotating like this. So it is rotating like this, means like this, okay. So this is what? This is anti-clockwise direction, okay, and this is what? This direction is your clockwise direction, right? Now make your right hand thumb, okay, make your fingers of the right hand, okay, fingers of the right hand, just point them in this particular direction. Your fingers of the right hand, the nails of the finger of your right hand, the nails of the finger of your right hand should point in this direction. Nails of the finger of your right hand should point in this direction, and in this case also the nails of fingers of your right hand must point in this particular direction. Then the direction in which your thumb points, your thumb will point in the upward direction, because this is going inside the plane, right? This is coming in from inside the plane and going again inside the plane, okay. You have to imagine in 3D. So your direction of thumb, according to right hand thumb rule, the direction of thumb will be this, okay, and over here the direction of thumb will be in the downward direction, okay. When you make your fingers of the right hand, your nails of the finger of your right hand point in this particular direction, the direction of thumb will be downward direction, and over here the direction of thumb was upward direction according to right hand thumb rule. Then s vector, clearly s vector has only two directions possible, right? S vector has only two directions possible, on either this direction or this direction, okay. Any other direction like this or like this is not possible for s. Any other such direction is not possible for s. So let us consider this direction to be positive and let us consider this direction to be negative. Then what will happen? When you write s vector and remove its vector sign, it is one dimensional. It is one dimensional. So plus minus. So if it is in the upward direction, then call it S, and when it is in the downward direction, call it minus S, right? Magnitude I am saying. Okay, so that's why the SI vector and plus SI vector has been converted into plus minus S. So ji vector equal to Li vector plus Si vector, and J vector will be J, when we take its magnitude, then what will happen, J equal to L plus minus S, because only two directions, this particular vector has only two directions possible. It is one dimensional vector, that is it has only two directions possible. One direction is positive, other is negative. So that's why plus minus has come over here. Okay, so hopefully you got this. From here onwards we will do in the next class. I am feeling very much tired. From here onwards we will do in the next class. Find I value and falana dimkana or etc., etc. We will do in the next class. Okay, so thank you very much.